just supports a long-held belief of mine that women are smarter than men. Okay, today we're going to be talking about the digestive tract. Now, clearly, the digestive tract is really nothing more than an elongated tubule that begins at the mouth and at the anus. Structurally, you can determine at least certain divisions by their gross anatomical appearance. Before we talk about the specific parts of the digestive tube, what I'd like to do is simply outline the overall general structure of the tube. And then we'll go back and talk about the unique structures that specify different components of that tube. So, again, what we'll do is start with the lumen and work our way outward through the wall of that digestive tube. The interior of the tube, that layer, is called the mucosa. And the mucosa is always lined by epithelium. And that epithelium can vary in different regions of the tube. Suffice it to say at this point that the mucosa is always lined by a layer of epithelial cells. Immediately below that epithelium is some connective tissue, and it's usually of the loose connective tissue variety. And this, if we put the epithelium here, immediately below it is a layer called lamina propria. This is, again, basically loose, fibrous connective tissue, and it can contain blood vessels, nerves, and a bunch of cells that you should be familiar with from our discussion of fibrous connective tissue. The outermost layer of the mucosa is an interesting layer of smooth muscle, and this layer is called the muscularis mucosae. Now, this muscle is relatively thin, and it has nothing to do with peristalsis, which is very pronounced movements of the gut. Instead, what the muscularis mucosae does is that it tends to wrinkle the mucosa, and that's about all its function is. It's very thin. As you will see, it's at its thickest in the esophagus, where it only measures about 700 micrometers in thickness. Everywhere else, it's considerably thinner. Okay, so the mucosa begins with epithelium underlaid by lamina propria, and its outermost extent is marked by the muscularis mucosae. Yes?
Where does the submucosa lie? Is it with the lamina propria?
I'm sorry,
The submucosa?
I'm sorry, the lamina propria is simple loose connective tissue, and all of the cells that we have discussed that take up residence in that connective tissue, like fibroblasts, lymphocytes, plasma cells, and so on, are to be found there.
Is it the same thing as submucosa?
No. Next layer, as we continue outward, is called the submucosa. Remember, the mucosa is separated from the submucosa by the nes muscularis mucosae. Okay, the submucosa is also nothing more than connective tissue. And there are more fibers here than there are in the lamina propria, but it's still a kind of loose connective tissue. And what is present mixed in with this connective tissue? Well, there may be some glands, there may be lymphatic nodules, there are blood vessels, and there are nerves. What you would expect to find in any connective tissue. Okay, now proceeding, yes?
Going back to the muscularis mucosae, what is the purpose of wrinkling the epithelium?
Bad word, purpose.
What's the function?
Yeah, much better. That may be involved in just exposing different parts of the epithelium more efficiently to whatever is in the lumen. It's a good question. I'm only supposing, I don't know this being absolute fact, but it clearly has nothing to do with peristalsis. Now, peristalsis is a function of the next layer as we proceed outwardly. Remember, we're going from the lumen to the outer surface. The next layer is the muscularis externa. Usually called simply muscularis. Don't confuse this layer with the muscularis mucosae. Remember, the muscularis mucosae is very thin. Muscularis externa is quite obvious and thick. And if you look at it carefully with a microscope, you can see that in most areas it consists of two layers of smooth muscle. An inner layer where the muscle fibers are oriented in a circular fashion. So the inner layer is circular. The outer layer, the muscle fibers are oriented longitudinally. Now, that is a way in which this is usually described, but in reality, both layers are probably a bit on the helical side. You know that little party favor that gets handed out, that so-called Chinese finger trap, you know, where you put your fingers in and can try to pull out, you can't get your fingers out? Well, you know the way the parts are woven together? That's essentially what is going on in the muscularis externa. Because of the orientation of the muscle, they can produce, these layers can produce peristaltic waves that move food substances forward down the length of the of the tube. Now, there is one place, that is in the stomach, where there's actually a third layer of smooth muscle. It is inside the other two, and it is oblique. You would never be able to tell it by looking at a microscopic section of the stomach wall. That third layer is obvious only if you do a gross dissection of the stomach and you peel off the layers of the mucosa, of the muscularis externa. You will find that inside the circular and longitudinal muscle, there's another layer which is sort of oblique, only in the stomach. And we'll come back to that in a few moments. Now, the last layer is sort of a peculiar one in a sense. It is called a serosa. Now, what the serosa actually is the mesenteric envelopment of various parts of the digestive tube, like the small intestine. You'll recall from gross anatomy that if you grab hold of the small intestine and sort of pull it, there's this thin sheet of material that seems to connect it to its neighbors. That is mesentery. It's simple squamous epithelium, and it covers those parts of the digestive tract that lie free in the abdominal cavity. Now, there are some parts of the digestive tract that don't fit that description. The esophagus, for example, passes through the thorax. It is not suspended on any kind of mesentery, so there's no serosa for almost its entire length. And in that case, we refer to that outermost layer that is outside of the muscularis interna as an adventitia. Now, to make this a little bit more complicated, you remember that there are some parts of the digestive tract that are retroperitoneal that they don't just hang there. For example, the duodenum and the rectum. On one side, they're covered by mesentery. On the other side, where they're against the body wall, there's just some connective tissue. So there's an adventitia there. So the same organ can have a serosa on one side, which is nothing more than a mesenteric investment, and on the side against the body wall, just some connective tissue, which we refer to as the adventitia. Everybody follow that? Any questions about that? Okay, this being the case now, this is the general plan of the digestive tube. Now, let's begin to look at it regionally. The first part, obviously, is the esophagus. If we look at the layers of the esophagus, beginning with the mucosa, immediately we see that the epithelium is different from the epithelium in any other part of the digestive tube, in that it consists of stratified squamous epithelium. This epithelium in let's say a newborn human being is non-keratinized. In other words, it's para-keratinized stratified squamous epithelium. Hope you remember what that means. What that means, of course, is that there are nuclei in the cells right on up to the very surface. Now, as one gets older, if you like to eat spicy foods, so I mean really strong spices, what happens is that those cells at the surface start dying, and you end up with orthokeratized stratified squamous epithelium. So the kind of stratified squamous epithelium that lines the esophagus is strictly an individual matter in human beings. Now, in animals, for example, that eat grass and leaves and all kinds of tough stuff, it's always orthokeratized. In animals that eat only soft tissues, it's usually parakeratized. The important thing to remember is it's stratified squamous epithelium. In the mucosa, below the epithelium, in the lamina propria, there may be some glands. These are esophageal glands, and these glands produce mucus. There's a much more abundant kind of esophageal gland, which is present in the submucosa. Remember, to go from the mucosa to the submucosa, we have to pass through the muscularis mucosae, which is a layer of smooth muscle. And it's in the esophagus, that layer is at its thickest. Nowhere else in the entire GI tract is the muscularis mucosae as obvious and as thick. It's not absolutely clear as to what is going on there. And a muscularis externa is also a little unusual in human beings, especially. The first quarter of the length of our esophagus, the muscularis externa consists almost exclusively of skeletal muscle cells. You remember, skeletal muscle cells are under voluntary control. As we go deeper into the esophagus, that muscularis externa begins to change, so that in the next quarter, the second quarter of the human esophagus, there is a mixture of skeletal muscle cells and smooth muscle cells. And then the last half of the human esophagus, the muscularis externa consists entirely of smooth muscle. Okay, so there's a progression from skeletal muscle to voluntary to a mixture of voluntary and involuntary muscle, and then finally involuntary. And you've encountered this. Sometimes you start swallowing something and it doesn't feel right, you sort of cough, and you can expel it. You're dealing with the skeletal muscle part of your esophagus. However, once the bolus of food has gone beyond a certain point, it's out of your control. And what seems to happen when you swallow a bolus of food is that the smooth muscle in the muscularis externa sort of opens up in front of it to allow passage and closes behind it. So the bolus of food will slide down, lubricated by the mucus being produced by the esophageal glands, and then finally gets into the stomach. If your esophagus stayed open and patent all the time, and word splash. When it hits the stomach, it doesn't happen, obviously, because it's in a compartment like an elevator going down the esophagus. Okay, now, we said that the esophagus, because it is not suspended with mesentery, does not have a serosa. But remember that the esophagus passes through the diaphragm and leads down into the abdominal cavity for a couple of inches. And for those 2 inches or so, or 1 inch, there is a serosa. There's a mesenteric lining on the surface. And that's really all that there is to the esophagus. It's really quite a simple structure. The only complexity is in the variation in the muscularis externa. Okay, now we move on to the stomach. Now, the stomach, you remember, is this big sac-like structure, which from your gross anatomical observations all looks the same. However, if one can take sections of the stomach wall and examine them, it turns out that there are regions within the stomach wall. And we can sort of very crudely indicate how these are put together. If this is the stomach with the esophagus here, the top part of the stomach, where it sort of meets the esophagus, is called the cardiac portion of the stomach, where it sort of makes the transition to the small intestine is called the pyloric region, and the main body of the stomach is called the fundic stomach. Now, we're not going to bother to go through the various differences between these regions. We'll just talk about the fundic stomach, which sort of is indicative of the stomach wall as a whole. Again, if we apply our analysis to the stomach wall, starting with the mucosa, it is lined by simple simple columnar epithelium. Simple columnar epithelium. What's different about these cells is that they make mucus. These are mucus cells, but they're not goblet cells. They're not shaped like a goblet. They're simple columns, and they have some mucus up at their top. That mucus is extraordinarily important because it helps to protect the stomach against the secretions of the stomach. Question always arises, why don't the enzymes that are being made by the stomach digest the stomach itself? Well, a mucus helps to protect the wall. Very important structure. Now, if you were to look at the surface of that epithelium with a scanning electron microscope, you would see that there are openings all through the epithelium. And what is going on is that the epithelium invaginates so that what we're seeing is an inward, an inpouching of the epithelium. The first part up here, close to the surface, is called gastric pit. Below that, the remainder is a gastric gland. These are all in the mucosa. It's just an inpouching of the epithelium into the lamina propria and extends all the way down to the muscularis mucosa. Now, it's the makeup of these glands and pits which is very interesting. If we start up at the top, remember we said that the pit is actually an inpouching of the surface epithelium. Remember, the surface epithelium makes mucus. These are mucus cells. Well, the cells in the pit also make mucus, but it's of a different kind. And I will show you a picture to show you how the staining of the pit varies from the staining of the surface. It's a second type of mucus, all of which may be involved in protection. Now, as we continue down into the depth of the gland, a certain kind of cell becomes very obvious. These are cells which are very eosinophilic. That is, in an H&E preparation, these cells have a pink to red to orange cytoplasm. And there's a lot of them. And they extend not to the bottom, but relatively close to the closed end of the gland. These cells, which are found all along here, like so, are known as parietal cells. Again, this blackboard refuses to take the chalk, so it ends T-A-L. They're parietal cells. These cells are extremely important cells. We now know that these are the cells that produce hydrogen ions that ends up becoming part of the HCl that is present in the stomach. I hope you're aware of the fact that the contents of your stomach have rather high acidity. And it's hydrochloric acid, which is the acid. It is produced by the parietal cells. And the structure of the parietal cells is related to their ability to secrete hydrogen ions. We didn't know too much about the structure of these cells until the electron microscope came along. And now we know that they're very unusual in terms of their structure. If this is one of the cells, it turns out that they have these invaginations of their surface to produce what are intracellular canaliculi. Intracellular canaliculi. When these cells are not secreting, they have huge number of fine tubules filling the cytoplasm. Literally thousands in the cell. Now the cell is stimulated to secrete acid. And what seems to happen is that these tubules turn inside out and form microvilli in these canaliculi. Okay, it's like you take a sock and you turn it inside out. And somehow that promotes the release of hydrogen ions. So in the electron microscope, it becomes possible to easily differentiate between a secreting parietal cell and a resting parietal cell. It depends. All you have to do is look at those canaliculi. If the canaliculi are sort of naked, it's a resting cell. If the canaliculi are filled with microvilli, which are the reversed tubules, then it's a cell which is actively producing hydrogen ions. Now that sounds like it should be enough, that these cells are more than earning their keep. Turns out they have a very important secondary function also. I'm sure you've all heard of a condition called pernicious anemia. Do you know what that is? That this is an anemia based on the fact that vitamin B12 is not being absorbed properly. And vitamin B12, you may recall, is necessary in the synthesis of DNA. If you can't make DNA, you can't make blood cells. And it leads to anemia. Now, this disease was recognized, way back in the early 1800s. Nobody knew what caused it. After a while, it became obvious that there had to be something in our diets that was missing, that was not getting into the body, that was necessary for the production of DNA, although nobody knew anything about DNA in those days. But it was clear that there was some kind of a dietary factor that was missing. Well, you know how they used to treat pernicious anemia back in the 1920s or so on? One of my professors was a medical student back in those days, and he told us what they used to do. They would get medical students to volunteer, they would eat a liver meal, and then they would have their stomachs pumped, and the contents then were centrifuged to get rid of any chunks of undigested material. The supernatant was then filtered through gauze to get rid of any solid material, and they ended up with sort of this juice. They would put that into capsules and give it to people who had pernicious anemia. And it worked. They got better. Well, this was the way that this went on until vitamin B12 was discovered. And we now can make vitamin B12 in industrial batches using bacteria. And what they've been able to do is circumvent this whole problem. You can take vitamin B12, put it into a syringe, and inject it. You don't have to worry about absorption anymore. So pernicious anemia has pretty much disappeared in the Western world. But it wasn't that we were not getting enough vitamin B12. It's that parietal cells were not making a factor that allowed the absorption of vitamin B12. This factor has been isolated, and we now know a great deal about it. It is called intrinsic factor. Intrinsic factor is a material that allows or promotes the absorption of vitamin B12 into the body. Okay, so pernicious anemia is no longer the scourge that it once was. People used to die of it, and especially women who seem to develop this problem more than men did. Probably an immune response, and our immune systems make a mistake and turn off the machinery that makes intrinsic factor in some individuals. It was not an uncommon condition. Something like 1 in 1,000 Americans used to develop that back in the old days. So it's parietal cells that come to our rescue. Okay, so the second function then of parietal cells is to make intrinsic factor. First function, they pump out hydrogen ions. Okay, I should mention that the pinkness of staining that one sees in these cells is due to the fact that these cells contain a large number of mitochondria. And mitochondria tend to stain pink. Okay, let me make some introductory remarks then about the intestine, and then we'll take a break. Now, obviously, aside from digestion, a major function of the small intestine is absorption of digested food. Now, you realize, of course, that absorption depends on surface area. In other words, the more surface area that is available for absorption, the more efficient this function is going to be. So a goodly part of the small intestine is devoted to surface amplification to increase the available surface for absorption of digested foodstuffs to take place. Now, the first of these consists of transverse folds. How can I illustrate that? If, say, my sleeve here is the wall of the intestine, if we make some folds that extend inwardly, going in a circular fashion, we do increase the surface area, not by a huge factor, but by an obvious one. And so if this is the wall of the intestine, in a longitudinal section, you would see cross sections of the folds. These are not finger-like, these are folds that run about halfway around the circumference of the tube. Again, think of it as like a sleeve with some folds on the inside. These structures were originally called the valves of Kirkring. Since there is now a tendency to get away from eponymic designations, they're also known as Plancky fold circularis. All right, so these are folds that run about halfway around the interior of the small intestine. They increase the surface area. The second way in which the surface area is increased is that the mucosa is thrown into finger-like structures that are on the surface, like so. These are structures which I hope you were able to observe in gross anatomy, the so-called villi. Villi are finger-like structures that extend into the lumen. There are literally hundreds and hundreds of these. If you got a chance to look at the lining of the duodenum with a magnifying glass, just an ordinary cheap little magnifying glass, you would have seen what looked like little stubby structures that form like the nap of a carpet. And if you would run your finger across it, it would have a kind of velvety touch because of those little fingers. The presence of these villi really increases the surface area tremendously. Now, the third way in which the small intestine increases its surface area is by the nature of the lining epithelial cells in the mucosa. These cells, most of them, have microvilli on their surface. Hope you remember about microvilli. Remember these are these finger-like extensions of the apical cytoplasm. And one cell can have several hundred of these. So by the time we are finished between the Plancky circularis, the villi, and the microvilli, we have enhanced the surface area of the small intestine quite enormously. Okay, let's take a break and then we'll talk about the cellular composition of these structures. That I had in my notes some numbers which I meant to mention, but please don't write these down. But in terms of the increase in surface area that these structures that we spoke about can produce, the Plancky increase the surface area about threefold. You don't have to remember these numbers. Villi about tenfold. The microvilli about 20-fold. if you multiply this out, this means that the surface area is increased 600 times by the presence of these structures. And obviously, this is going to increase the efficiency of absorption. Okay, what is the story of the epithelium on these various structures? Well, the most abundant cells are tall, simple columnar epithelial cells that have microvilli up on their surface. These are absorptive cells, and you may recall that such cells have what is known as a striated border. These are the most abundant cells that are found in the lining epithelium. In addition, there are some goblet cells. You remember that goblet cells are mucus cells that produce a batch of mucus droplets that distorts the cell so that it ends up being shaped sort of like a wine goblet, a larger upper portion where the mucus is stored, and then a thinner stem-like portion where the nucleus and other organelles are present. And then there's another cell type that's very difficult to see in ordinary preparations. And these cells were originally called argentophin cells. Argentophin. You may recall that the French word for silver is argent, and these cells are called argentophin cells. Actually, those cells were discovered way back in the 1800s, and different histologists used different kinds of staining mixtures to reveal these cells. In an H&E prep, they're almost invisible. They're very hard to see. And there were piles of histologists who came up with different staining protocols to reveal these cells. Well, in order to refer to these cells without going through a long story on the staining, the names of the various authors got associated with these cells. Now, don't write these down, but just let me give you an example. These cells were called Heidenhain cells, Nicholas cells, Nussbaum cells, Kulczycki cells, Chacho cells, Schmidt cells, Werther cells, all named after people who had used a different staining protocol to reveal these cells. Well, it turns out they were all right. It turns out that there are probably 8 different kinds of cells that are present in the lining epithelium in the small intestine. Now we know a lot about the histochemistry of these cells, and they all carry out a similar function. They all make hormones. These are all endocrine cells, but they all go through a similar biochemical process. And these cells are known as amine precursor deamination is a long, long way of describing cells, and these cells are now referred to by the first initial in these words. They're known as apud cells, A-P-U-D. The only reason I mention this is that every once in a while, one of these cell types might become malignant. And a tumor of such cells is usually referred to as an apodoma. Now, if you were suddenly presented with that term, apodoma, you know that oma is usually a suffix that's appended to a type of tumor, like a hepatoma or a seminoma. And you would wonder, what the hell's an apud that's turned into an oma? It's one of these little endocrine cells that are present in the epithelium. They're very difficult to see in an ordinary preparation. You have to use special staining techniques. I will show you a picture in just a moment to show you what these things look like. It almost looks like little fly specks on the section. They're really difficult to observe. Okay, so we've got all of these cells lining the surface. Now, remember we mentioned that there are villi all through the small intestine. Turns out that in between the villi, there are invaginations down into the mucosa, so that if we were drawing it, we would have a situation like this. In between the villi, there are these invaginations. It would be like, I would pretend my hand is the epithelial wall, my fingers are the villi, and in between my fingers are invaginations down into my palm. These invaginations have a name. They're called the crypts of Lieberkuhn. Crypt of Lieberkuhn. Now, it turned out that the cells that make up the crypts of Lieberkuhn are very interesting. Up at the top of the crypt, there's a bunch of dividing cells, cells that are engaged in very rapid mitosis. These cells are constantly generating new absorptive cells and goblet cells. These newly formed cells are forced up the sides of the villi as they multiply, and they sort of glide up to the top of the villi, and then they get shed. This takes about, in a human being, takes about 4.5 days for a cell that is newly born down in the crypt to make its way up to the very top of the villi and then get shed. Now, some calculations have been done on this sort of thing. In a rat, for example, a rat exclusive of its blood consists of about roughly 64 billion cells of all kinds. Now, if we look at what's happening in the intestine with these new cells being gliding up the side of the villi and being shed, roughly on a daily basis, something like 1.3 or 1.4 billion cells are shed daily. Now, if you think about it, that means that in 20 or 30 days, a rat has shed the equivalent of its entire body, enough cells to make a new rat. Seems like an awfully wasteful process. Why? Why do you think that this process goes on? It's happening to all of us. As you sit here, you've got these cells gliding up and being shed. Well, why? Well, I don't think any of you are old enough to remember this phenomenon, but years ago, whenever you went into any kind of public building, a department store or whatever, that were lit by fluorescent lights, some of the lights were always flickering. Always. Never failed. You never see that anymore. Why? Because in the department stores, they know what the half-life of a fluorescent bulb is, and they automatically change those bulbs for new ones so that the bulbs are always perfect and working. Well, when you consider that your gut is the portal of entry, or the potential portal of entry for all kinds of bacteria, you want to make sure that every cell in the lining mucosa is working at its utmost. It's doing its job. You don't want any senile old cells there that could be a point of entry for pathogens. So apparently, the constant renewal of the gut wall helps to ensure your safety against invasive bacteria, protozoa, fungi, whatever. But it's an interesting phenomenon that happens. Okay, so we've got at the top or into the middle of the crypt of Leverkusen these dividing cells. And these dividing cells, as soon as they're born, begin this upward journey to get rid of older cells. Some of the cells go in the opposite direction, down towards the blind end of the crypt, and they accumulate here, right down at the bottom. And they're very easy to identify because they contain large, very red staining granules. So these cells are down at the blind end of the crypt. And these cells are named after their discoverer. They're called Paneth cells. What do Paneth cells do? Well, if you think about it, crypt of Leverkusen is a great place for bacteria to set up light housekeeping. It's nice and dark, it's moist, there's a continuous supply of substrates, so bacteria could get packed down into these crypts and cause trouble. Well, the Paneth cells don't let them. Well, how do they do it? Well, several ways. First of all, they can recognize bacteria that have been colloquially buttered by IgA in the saliva as foreign intrusive bacteria. And what they do is they phagocytose these bacteria. They literally reach out, take them into the cell, and kill them. Those granules that you see contain lysosomal enzymes, and the Paneth cells kill bacteria. So they maintain basically the sterility of the crypts. Okay, now, how do we distinguish the parts of the small intestine from one another? You will recall from gross anatomy that the small intestine has three distinct components: duodenum, jejunum, and ileum. You can easily tell these apart at the microscopic level, although grossly you can't. How do you tell them apart? Well, the duodenum contains glands in their submucosa. These glands are called Brunner's glands. That's B-R-U-N-N-E-R'(S). Brunner's glands. Brunner's glands are sort of interesting because, first of all, what they do is they help to neutralize any acid that was carried over from the stomach into the small intestine. Remember, in the stomach, the pH is somewhere quite low, somewhere around 1 to 2, whereas most of the enzymes that work in the duodenum have to work at a pH of about 8. So it is the secretions of Brunner's glands which neutralize the acidity. They have another very important function that was discovered, not all that long ago, back in the 1970s, I guess. It turns out that Brunner's glands produce growth factors. I don't know if growth factors have ever been discussed in any of your courses, but they're very important. They were discovered by this wonderful woman, Rita Levi-Montalcini, and her grad student, Stanley Cohen. Levi-Montalcini was a very interesting person. She ended up winning a Nobel Prize for this discovery, and she lived longer than any Nobel Prize winner ever has. She was almost 104 when she finally shuffled off this mortal coil. Anyway, I met her a number of times, and even when she was well into her 80s and 90s, she was coming to meetings and so on, and she was still a very handsome woman. I'm sure that when she was a young woman, she must have been a knockout. really good looking woman, but very imperious, you know. By the time I met her, it was like she was almost the queen of salivary glands. Anyway, she did some wonderful work, and it turned out that Brunner's glands were the first place where they were able to demonstrate the production of nerve growth factor. And that has led into all kinds of new discoveries in molecular biology. So Brunner's glands play an important role in the history of biology. Okay, so we can recognize the duodenum by the presence of Brunner's glands in the submucosa. Now, let's skip the jejunum and go to the ileum, the last part. The way one can identify the ileum is by the presence in the submucosa of what look like lymphatic nodules. And they're in a sort of a special relationship. If this is a cross-section of the gut with the mesentery here, there is what look like a series of lymphatic nodules. They're not really nodules. In three dimensions, they're sort of shaped like a cigar, but in cross-section, they look like typical nodules. These structures are named after their discoverer. They're Peyer's patches. I don't know if you heard about those in your immunology lectures, but they usually get mispronounced as Peyer's patches. These are lymphatic nodules, and their importance is that they make the lymphocytes that end up going up into the thymus to make T lymphocytes. Anyway, they're important immunological tools. Okay, so we said that the duodenum has Brunner's glands, the ileum has Peyer's patches, the jejunum has neither. It's that simple. Okay? Jejunum, Brunner's glands, duodenum, Brunner's glands, jejunum, nothing, ileum, Peyer's patches. That's it. Okay, and that really is all that there is to the small intestine. I mean, there's a lot of other stuff which we can get into, not necessary. Let's just continue on our journey, and the next structure that we would come to would be the appendix. And there's one very easy way to identify the appendix, and that is if you have a cross-section of the appendix and you can see the lumen is completely surrounded by lymphatic nodules, different from what goes on in the ileum, where Peyer's patches are on one side. In the appendix, there are lymphatic nodules all around the lumen. So the appendix actually is an important lymphatic organ. And you know, it can easily get infected, but these days with antibiotics, surgery is pretty much ruled out for appendicitis. Anybody here who doesn't have his or her appendix? You're one of the lucky ones. Back when I first started teaching, practically everybody in the class would have raised his or her hand. It was really a common surgical procedure. Used to send surgeons' children to colleges, you know, because of the money that they used to make on that. Okay, let's just continue on to the colon. And again, let's just simplify it. Colon has no villi. It does have deep crypts of Lieberkühn. And the most important cells that are present are goblet cells. Huge number of goblet cells. Now, it turns out that the muscularis externa is a little different in the colon. Remember we said that in the small intestine and preceding parts, it forms, the muscularis externa forms a complete sleeve around the tube, an inner circular and outer longitudinal layer. Well, in the colon, the longitudinal layer is divided into 3 longitudinal bands, so that if we had a cross-section of the colon, the external layer, the longitudinal layer, is divided into bands, and these are the structures that are called the tinea. I'm trying to remember how to spell these things. The tinea coli. T-A-E-N-E-A. Tinea coli. And it is the function of these bands of muscle that keeps the colon in that kind of sacculated appearance. You remember that the colon appears to be pinched in at intervals. It is because of the tonus of the tinea coli. If you were to snip those, the colon would open up like a telescope. And then finally, you know, the major function of the colon is resorption of water. Finally, we get to the rectum, and there's really not much difference between the structure of the rectum and of the colon. The major problem there is that there is only a partial serosa. Now, there are other structures there that are very important, and I just want to read something to you that I haven't come across long before anybody in this room was born. The prime objective of hemorrhoidectomy is to remove the offending varicosity with as little damage as possible to the patient. You can damage, deform, ruin, remove, amputate, maim, or mutilate every structure in and around the anus except one. That structure is the sphincter ani. There is not a muscle or structure in the body that has such a keenly developed sense of alertness and ability to differentiate between various situations. They say that man, through the clever use of his hands, has succeeded where the animals failed. Yet, when compared to the hands, the sphincter ani is far superior. If you put into your cupped hands a mixture of solid, fluid, and gas, and then through an opening at the bottom, try to let only the gas escape, you will fail. Yet the sphincter ani can do this. It apparently can differentiate between solid, fluid, and gas. It apparently can tell whether its owner is alone or with someone, whether it's standing up or sitting down, whether its owner has his pants off or on. No other muscle in the body is such a protector of the dignity of man, and yet so ready to come to his relief. A muscle like this is worth protecting. Hey, I always found that very amusing. Just goes to show that some MDs have a great sense of humor. Let me show you some pictures now. Can somebody operate the projector, please?
Hey, Dr. Chandler?
I have a question.
So, does the appendix have a purpose?
Can't hear you.
Does the appendix have a purpose?
I wish you would not use the purpose. Yeah, it's a lymphatic organ, that's all I can say. It is an evolutionary remnant from, if you go back down through the mammals and so on, they all have an appendix. Probably its most important function is immunological. Okay, this basically is a drawing of a cross-section esophagus. And you can see because of the heavy musculature, the lumen has this kind of scallop look. There is a stratified squamous lining, and the mucosa extends from this epithelium through the muscularis mucosae, shown here as this thin band. Then submucosa, muscularis externa, and adventitia. The next slide. This is a high magnification of the epithelium of the esophagus. And you can see here that there are nuclei right on up to the surface. So this is a parakeratinized, stratified squamous epithelium. The next slide. This shows the second quarter of the length of the esophagus, and these larger cells here are skeletal muscle cells. These smaller cells are smooth muscle cells. Eventually, smooth muscle will take over completely. The next slide. This is a low magnification of the stomach. And up at the top, you can see the mucous cells that line the stomach. And then these are the glands that extend all the way down to the muscularis mucosae, which is this band right here. And then there's the muscularis externa. Now let's look at higher magnifications. The next slide. Oh, this is done with a scanning electron micrograph. This would be as if you were inside the stomach and looking outward. And here you can see the openings of the gastric glands. The next slide is just a higher magnification to show you that it's really an opening that extends down into the wall. These are all mucus cells that are present in the lining. The next slide. And here you can see some pit cells. Well, first, this is the beginning of the gland, and the cells have the same staining as the surface. And then we come to other mucus cells, which aren't stained at all. These are what are called mucous neck cells. they make a different kind of mucus than these cells. The next slide. Here, again, if we look at the left is the surface of the stomach. And you may notice as you look down these glands that there are a lot of cells that have sort of a pinkish color. Those are all parietal cells. The next, and here, although I'm sorry that the contrast is not very good on this, you can see these pink cells. These are all parietal cells. The next slide. Here, perhaps a somewhat better rendition of these cells here. And the next, this is a resting cell, parietal cells that's seen in the electron microscope. Here is a cross-section of an intracellular canaliculi. And you see that there's only a few microvilli in there, whereas the cytoplasm is filled with these tubules. And there's a number of mitochondria as well. Since these cells are pumping out hydrogen ions against a concentration gradient, it requires work, ATP, and it's the mitochondria that are making it. The next slide is simply a drawing to perhaps clarify what you're looking at. Secretory canaliculi in cross-section with very little content, and these tubules that fill the cytoplasm. So this is a resting parietal cell. The next slide is a stimulated cell. Next, please. And in this drawing, you can see that the canaliculi are just filled with microvilli, and there's another one over there, and that there are not so many tubules in the cytoplasm. The next one. Okay, let's see. This shows you some parietal cells, and that the cells all the way down at the bottom of the gastric glands. These cells, which I really should have said something about, are cells that produce the precursor of the major protease that is present in the stomach. They make pepsinogen, and when the pepsinogen moves up through the gland and passes through that acid-rich environment, it is converted to pepsin, the active form of the protease. Very strong protease. The next slide. This shows you some nerve cells between the layers of smooth muscle. This is what is known as Meissner's complex, for those of you who might have had a histo course. Not important for our purposes. Can we keep going? I think there's a blank, and then, oh yeah, before we leave that, here are some apud cells that have been stained with a fluorescent dye. These cells are in the stomach wall, and they produce the hormone gastrin, which Dr. Whittingham may have told you about. Just show you that there are such cells in the gastric wall. The next, and just keep going, one more. Okay, this is a longitudinal section through the duodenum, and you can see here the valves of Kirkring, and on their surface are many villi. The next is a scanning electron micrograph of the rat small intestine to show you these sort of finger-like structures which are villi, and you can see how these structures really increase the surface area of the tube. The next slide. And here, what's been done is that the blood vessels within the villi have been filled with plastic, which is allowed to harden, and then all the soft tissue was removed. And what you're looking at is a plastic model of the vasculature of individual villi. So you can see that material that is absorbed through the villi finds a ready home in the vasculature, and it will be carried to the liver for the most part. The next slide. Now, this is a light micrograph showing the size of two villi that are right next to one another. And the important thing here is the striated border. Those are microvilli. The next slide shows them even better. This has been stained with the PAS technique, which has stained a couple of goblet cells and the striated border. You see the striated border seems to have two layers, and the reason for that becomes clear in the next slide, which is, now, this is a high magnification of the striated border, and you can see individual microvilli here. They all have a filamentous core, and the next slide is a cross-section through these microvilli. You can see the lining plasma membrane, and these dots here are cross-sections of filaments, probably actin, which is involved in the movement of these structures. The next slide. Here, that fuzz coat has been stained, and you can see here it's very heavily stained, and here much lighter because of the presence of the cytoplasm. So that's why it looks like two layers. This fuzz coat is very important in protecting the gut against the friction produced by bacteria and whatever else happens to be in the lumen. The next slide. This is a structure which I should have mentioned. It'll never come up on a test because I think I'm the only one in the United States who even knows about this. But in human fetuses, during development, there's always at the tip of each villi, there's always a collection of apewood cells. These are called Sege's cap, named after the discoverer. And what's really amazing about this is that if you were to add all of the Sege's caps together, they produce a volume greater than the endocrine pancreas. So they must be very important during fetal development. And yet, I have yet to encounter an American histologist who knew about them. They're not going to be on any exams, but you should know that there is such a structure. Next slide. This is a slide that shows openings into the crypts of Lieberkühn, and you can see how many there are here. And then between some villi. The next slide shows you the bottom of one of those crypts. You notice that there are these cells with those intensely eosinophilic granules. Those are Paneth cells. Above are cells that are dividing or undifferentiated. The next, and this is again a drawing that shows the presence of Brunner's glands here in the submucosa. Muscularis mucosae muscularis externa, in between submucosa, and there are Brunner's glands. Next slide. This is a real micrograph showing again the villi and the muscularis externa, submucosa with Brunner's glands. So this must be the duodenum. Next slide. Just a higher magnification of these glands. And here you can see some wisps of the muscularis mucosae, indicating that we're now down in the submucosa. Next slide. Here we're into the ileum, and here are some Peyer's patches. Now remember that the jejunum has neither those Brunner's glands nor these structures. The next slide. This is a drawing of the appendix, and the important thing is the presence of lymphatic nodules all around the lumen. Next. This is the colon, and you can see there are no villi, but there are these deep crypts, and all of these cells that look blank are goblet cells because the mucus has not been well preserved or stained. Notice how much mucus there is there. The next. Okay, and then I think this is the last slide. This is an epoxy section of the colon, and here are some apo cells. And you can see that they would be very difficult to find in an H&E prep, especially if these granules stain eosinophilically. In this kind of a prep, they're black, so they're easy to see. Again, some goblet cells and the like. Is there another slide? No, I guess that's it.